So we are finishing out the content from chapter 12 today. We've only looked at section 12.5 in chapter 12, but there is plenty in there to keep us busy for our session today. I wanted to start with an example that is just a review of a problem we did look at on Tuesday, which is testing the hypothesis that the population correlation coefficient is equal to 0. Right, so unlike, say, where we're doing hypothesis testing about a population mean, and the test procedure always looks the same, when we're dealing with correlation, we actually have two different procedures depending on the exact formulation of the null hypothesis. If we're testing for a 0 correlation, we implement it in one way, and if we're testing for a non-zero correlation, we implement it in a different way. Now, we looked at testing for 0 correlation on Tuesday, but let's run through one more example. So we have a sample of size 24 from a bivariate normal population. For that sample, we observe a correlation of 0.52, and we want to test whether the sample evidence is still consistent with the population correlation being equal to 0 at the 1% level of significance. So when you're testing for 0 correlation, the test statistic you use is big T, defined as the square root of sample size minus 2 times sample correlation over 1 minus square root of sample correlation. So just plugging in all my observed values here, and this will give you a test statistic of 2.855 if you do that implementation. Now, we're testing against the general alternative here. So our alternative hypothesis says correlation is not equal to 0. So we need to do a two-sided test. Like effectively, we're using notation T for the statistic because it follows a T distribution with n minus 2 degrees of freedom. So we're referencing a T22 distribution. And for a two-sided test, our p-value is given by the area in both of the tails. So to the left of the negative value associated with the test statistic and to the right of the positive value associated with it, which in this case means our p-value can be calculated as 2 times using the TCDF function on your calculator, lower bound negative infinity, upper bound negative 2.855, degrees of freedom 22. So the TCDF, that calculates the left tail area for us, multiplied by 2, exploiting symmetry of the T distribution. So we get a p-value of 0.0092. That means since we're using a 1% level of significance, our p-value is less than alpha, which means we reject the null hypothesis. And so our conclusion would be that the sample evidence is consistent with the correlation being a value different than 0. So effectively, we're saying there is some measure of linear association between the two variables. I have a question about the degrees of freedom, and yes, degrees of freedom do not change depending on how the alternative is formulated. So if you're testing that the correlation is equal to 0, it will always be n minus 2 degrees of freedom. The form of the alternative here is not going to affect that. So for this specific test, always n minus 2 degrees of freedom. Okay, and there were some very similar examples in the Tuesday session if you want to revisit those. Now, the next one is still related, except here we're going to revisit the idea of a rejection region. So we're assuming that someone takes a sample of size 25. They want to test the hypothesis of zero correlation against a two-sided alternative. And we want to find the rejection region of this test at the 10% level of significance. So effectively, we're saying we know we're working with a t distribution with 23 degrees of freedom, sample size minus 2. And we want to know what the boundary points are for this t curve, right? What is the value negative t and positive t that we would use to reject? Now, if we're at the 10% level of significance, that means the area in the tail is going to be 0.05. So our critical value here is going to be a t value with area to the right 0.05 and 23 degrees of freedom. So you would use the t inverse function. Area would be equal to 0.95 because the function always uses area to the left, 23 degrees of freedom, which gives us 1.714 when I round to 3 decimals. So we can say that our rejection region in this case would be any time the absolute value of our test statistic exceeds 1.714. That's what the rejection region looks like in terms of the test statistic. This, remember, t equal to square root of n minus 2 times r over square root of 1 minus r squared. That's the statistic underlying all of this. So that's rejection region in terms of the test statistic, but we can convert it to a rejection region in terms of the sample correlation coefficient. Right? Effectively, we just want to know if the absolute value of t is greater than or equal to 1.714, what does that tell us about the sample correlation coefficient? Well, that means square root of this case 23 times the absolute value of r over square root of 1 minus r squared. That has to be greater than or equal to 1.714. So I can just write an equation in terms of r. So if I divide by square root of 23, I get 0.357. And now it's always cumbersome working with an absolute value, but I can just get rid of that by squaring both sides. So I can have r squared over 1 minus r squared is greater than or equal to, if I square the right-hand side, I get 0.1274. So this is an easy enough equation to solve. I'm not going to walk through those steps. Make sure you're comfortable doing that. But you can solve here and find r squared has to be at least 0.113. Which means if we take square root again, go back to absolute value, if you calculate a correlation coefficient and in absolute value, it's greater than or equal to 0.336, this would be an equivalent rejection region. So at a sample of size 25, this tells you what the threshold is at which point you would consider a correlation value to be significantly different from 0 at the 10% level of significance. So it's just kind of inverted the idea, and we've looked at a rejection region this time instead of how we would do it with a p-value. Any questions about this problem? Okay, let's look at 12.8. So this time we have a sample of size 18. Our sample correlation is 0.312, and we want to test the null hypothesis that the population has a correlation of 0.4 against a two-sided alternative, and we want to do that at the 10% level of significance. So now we're going to use a different test. If your null hypothesis has a correlation different than 0, it becomes a much more involved process. We have to transform our correlation coefficient to what I'll call the V scale. We have this transformation V is equal to 1/2 times the natural log of 1 plus R over 1 minus R. So we sub in our sample correlation coefficient. And if you do this calculation, you'll get 0.323. What you'll notice with this specific transformation, like we didn't shift very far away from where the sample correlation was. The closer you are to 0, the closer this function is to the identity function. So if you're close to 0, it almost doesn't change the correlation coefficient, but the closer you are to +1 or -1, the more nonlinear the transformation becomes and the further away it is from the identity function. So this is the transformation we need for our sample correlation coefficient. Now we also need to calculate the mean and the variance of the test under the null hypothesis. So to emphasize that I'm using the null hypothesis value, I'm going to call them mu naught and sigma naught squared. Mu naught is exactly the same transformation, except using the value under the null hypothesis. So this would be natural log of 1.4 over 0.6, half of that. That gives us 0.424. The null variance is easier to calculate. That's just 1 over n minus 3. And that gives us, in this case, 1 over 15. So this lets us now calculate a z statistic. You just take that observed v, subtract mu naught, divide by sigma naught. So in this case, 0.323 minus 0.424 over square root of 1 over 15. And this is negative 0.391. Okay, so we're doing this against a two-sided alternative, which again means if we're looking at our bell curve, we have negative 0.391. We also have the positive equivalent of that, and two-sided test means our p-value is the area in both tails. Now, z-test means we're using a normal 0-1 distribution, but it is only an approximation. And the quality of the approximation depends on the sample size, which is not very large here, so there is some or it's questionable how accurate this will be because the sample size is small. But our p-value will be given by 2 times the normal CDF at negative 0.391. And if you do that calculation, this ends up being 0.696, which is much larger than the alpha of 10%. So we do not reject the null hypothesis, which in this case means the sample evidence is consistent with the population having a correlation of 0.4. Right, now part B is just asking us to do the exact same thing, except with a sample size of 60. And what you'll notice is neither the calculation of V nor of mu naught change because those don't depend on the sample size. The only place the sample size factors in is when we look at the variance. So we still have the same value for V, the same value for mu naught. And now sigma naught squared is going to be 1/57. That in this case will give us a Z statistic of negative 0.763. And again, two-sided alternative. So p-value corresponds to both tail areas. And that ends up being, in this case, 0.446, which is still larger than our 10% level of significance. So again, we do not reject the null hypothesis. So what is the point of looking at the bigger sample size here? Well, we would expect at a small sample size, say 18 in this case, that you wouldn't be able to easily reject the null hypothesis. Like, we're trying to figure out what means being close to the value under the null hypothesis. Under the sample size of 18, that sample correlation is still close to 0.4. But even if we're at a sample size of 60, 0.312 is still reasonably close to 0.4. What it really comes down to is the correlation coefficient is a highly variable quantity. So you need pretty big sample sizes to make definitive statements about what it can or cannot be. And yeah, I'm sorry if I missed this question a while ago, but someone just asking if the null hypothesis has a correlation value of non-zero, do you use a z-test? Yes. So your setup is, if the null hypothesis value is 0, you're going to use a t-test, and you don't need all these complicated transformations. In that case, you use this t-statistic, which is fairly easy to calculate from the correlation. If it's non-zero, then it becomes a lot more involved, because then you need to transform the correlation to this log scale, both your sample correlation coefficient and your null hypothesis correlation. And then you can calculate a z-statistic. But that's the procedure if the null hypothesis correlation is any value different from 0. Now, this exact same procedure allows us to construct confidence intervals for correlation coefficients. So let's say we have a sample of size 24. Our sample correlation is 0.52, and we want to construct a 99% confidence interval for rho, the population correlation. You start off with this exact same V transformation. You apply that to your observed sample correlation. So in this case, taking the natural log of 1.52 over 0.48, dividing that by 2, and I get 0.576. Now, if I want a 99% confidence interval, that means I need z of alpha over 2. So I would use my inverse normal function, area in this case equal to 0.995, and that gives me 2.576. Then there's kind of a two-step procedure to calculating the confidence interval. I first calculate an interval that, for convenience, we just call C1, C2. This is defined as V minus Z of alpha over 2 over square root of n minus 3, and V plus Z of alpha over 2 over square root of n minus 3. And you can see this is the same standard deviation, like the square root of n minus 3, that's the sigma naught value. So it's the exact same quantities showing up here. Now, if we do this here, the interval for C1, C2 that we get is 0.014 through 1.138. But that's not on the confidence interval scale or on the correlation scale yet. This is an interval on the V scale that we've calculated. So we need to convert it back to correlation scale. So we invert this log transformation, and what that looks like is it's the exponent of twice the value minus 1 over the exponent of twice the value plus 1. And you do that for both C1 and C2. Again, this is easy to do. It's just like a little bit tedious plugging all of that into your calculator. But what you get in this case is your 99% confidence interval, and it's an approximation because we're relying on the normal distribution here, ranges from 0.014 through 0.814. So you can see here, like, we observed a positive correlation of 0.52. But at a sample size of 24, there's still so much inherent variability that any value from very close to 0 all the way through 0.814, all of those are consistent with the data that we've observed. Essentially what this tells you is this gives us a range of which values we could test under the null hypothesis, and we would not reject the null hypothesis, anything from 0.014 through 0.814. So sample size of 24, like almost the only thing that's good for is really helping us figure out if the correlation is positive or negative. And even then, if this correlation value had been slightly smaller than 0.52, the interval would have spanned going into the negatives. So only if you have a pretty large correlation, either positive or negative, can you be sure that the sample is even telling you whether the correlation is positive or negative. Never mind identifying whether it's a weak, a moderate, or a strong correlation. So I think that's just an informative thing to keep in mind. Now we have one more, well, let's see, question first. And yes, if you are calculating a confidence interval for a correlation coefficient, you are always going to use the z-value or the normal distribution, but it will always be an approximation. So our last example problem just flips the problem on its head again. So we started with a sample size of 50. Someone constructed a 95% confidence interval, and we're given the interval, and we want to work back to finding the sample correlation coefficient R. Now, what was nice when we were working, say, with a confidence interval for the mean, is we knew it was symmetric around the value, and we could just average out the two endpoints and get the sample average. But with the correlation, no such luck. Thankfully, the way this is constructed, you do not have to work with both endpoints. You can just choose one of the endpoints and you can work all the way back to the sample correlation. So we're going to take the left endpoint. We're first going to solve for C1. From that, we can solve for V, and from that, we can solve for R. And because it's a 95% interval, we need the z-value of 0.025. Our z-value in this case is 1.96. So if we're solving for C1, we know the formula for the left endpoint of the interval is given by e to the 2c1 minus 1 over e to the 2c1 plus 1. That's equal to 0.046. So I know a little bit tedious, but easiest way I found to do this is to actually make a substitution. You don't have to do that, but I just set the e to the 2c1 equal to a. So just solving the equation a minus 1 over a plus 1 equal to 0.046, which if you solve that, you'll find that a is equal to 1.0964. So that's my e to the 2c1, which means my c1 value is 0.046. Again, remember this transformation in either direction. If we're close to 0, it's very close to the identity function. So in this case, not surprising that I go through all of this work and up to 3 decimals, the value is the same. But we haven't quantified what's considered close to 0 or far from 0 in this case. So you kind of have to go through those steps. Next, we're going to solve for V. So we know when we calculated C1, let me write it that way around. C1 was equal to V minus the Z value over square root of sample size minus 3. So we just plug in the quantities that we have. Which in this case will give us that V is equal to 0.332. So now we're back on the V scale. We finally have to convert back to the correlation scale. So here we know V was calculated as 1/2 natural log of 1 plus R over 1 minus R. So make sure you're comfortable again just going through the algebra here. If I take V, multiply by 2, take the exponent, that gives me that 1 plus r over 1 minus r is equal to 1.9425, and I can solve for r from that. You will get r is 0.32. So yeah, a little tedious here, but you can work backwards from confidence interval to the correlation coefficient. What was the midpoint of this interval? You know, maybe you're curious how far off the midpoint would be from the true value. In this case, the midpoint value of the interval is 0.298 to 3 decimals. So you can see taking the midpoint, I mean, puts you a little bit off. And the further the interval is away from 0, the more the discrepancy will increase between the midpoint of the interval and what the correlation coefficient is. And of course, if you had wanted to, you could have done this exact same calculation with the right endpoint. It should get you to the same correlation coefficient. So are there any questions about these correlation examples? So last thing I'll say for today is, let me see what question we have here. So let me just backtrack to this example. Someone asking, is it a coincidence that the left endpoint of the interval and the C1 value are the same? It's not a coincidence, but it's not always going to be the same. What's going on here is that the transformation that we're working with, when we are close to 0, that function is very close to the identity function. So if you're transforming a value that's very close to 0, up to 3 decimals, you're most of the time going to get back the same value. If we had done this problem with the right endpoint, if we transformed 0.549, you would have gotten a C2 value that was different from 0.549. So you really just have to go through the steps here, because you don't know in terms of this function whether you're close to 0 or not. Okay, so test 3, it will be available on D2L on Monday. I do not have the exact time on me. I think I put a time on the information I sent out, but it will be uploaded on Monday, and you will have through Wednesday to complete that, if memory serves me correctly. So it'll be available at some point on Monday. It will be a shorter test than the previous one, because there's less material being covered on it. So it will not have more than 4 questions with parts. And so because it's shorter, once you start taking it, you're going to have 90 minutes to complete and upload it. And the content on the test, just 2 things. Chapter 10, specifically sections 10.1 and 10.2. This is the ANOVA test, as well as the Tukey procedure for identifying differences after the fact. And then chapter 12, where we only looked at section 12.5, this is correlation. Now, as you know, there's a lot that went into this. So it's hypothesis testing, it's confidence interval construction, it's calculating correlation coefficients, it's kind of being able to ascertain from scatter plots whether a correlation appears weak or strong, at least relative if you have a few of those to compare. But this is the only content you have to prep for the test next week. I will put up some practice problems. I'll have those up probably by lunchtime tomorrow for you to work through. And if you have any other questions, just let me know.